Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome to our course on Introduction to Micro Machining Processes. In the last class we have seen one example where desktop cut is playing important role in the cutting of a brittle material, and we have seen that how this signature can be captured by means of measurement of forces, because we are not able to get the visual information of this particular cutting operation throughout the machining. This is what we have seen here. It is a high speed camera picture, and that is many times difficult to incorporate in the actual machining or the production. This is for the research purpose we can get this information, but actual thing what we can get in practical situation is the force signal or some other signals by which we can monitor the status of the cutting tool and the workpiece material. So, this way we have understood that force data can be one of the important signatures of this machining operation, where you can get some insight of the operation, whether it is going perfectly right or there are some problems in this case. So, now let us see what are the different mechanism by which the material is removed in alloys. So, now if you see, this is one of the alloy and there are two different phases available. So, this is the first phase and this is the bulk material, and now what happens that suppose this phase material is hard, okay, and bulk material is little bit soft. Now, you are cutting a material, this material. So, when your tool is moving in this direction, now this is the location of the soft material, and then suddenly you encounter a face of this particular alloy where the hard is the face. So, now when you are reaching this location, at that time whatever the force signature you are getting here, that will be suddenly shoot up because you are coming across this hard grain and you have to cut or you have to pull out this grain. So, many times what happens that suppose the grain is located something like this, that very small amount of portion is located below this particular area and your tool is at this location. So, at that time what time the whole grain will be pulled out, because it has a high tendency to be a part of the chip compared to the part of the workpiece material. So, instead of a straight line, what you will get, the machine surface will be something like this, and you can consider this one as a pull out. So, this will many times happens in the metal matrix composite, that is shortly called the MMC, where you are putting some type of metals in terms of some type of small grains or something like that. This is also considered as a alloy. So, now this is happening in, so here force variation is very large, because initially you are cutting in a soft zone, suddenly hard material comes into a, then again soft material, then hard material, and the location of this hard material also creates a different mechanism, whether it is a, what is the location, how much percent it is inside of this bulk material and how much is onto the chip side, that is called uncut chip thickness part. So, those all things plays important role in cutting of this alloy material. So, let us go into more detail. The all alloys have several phases present with the different material properties. Different material properties is mostly related to hardness, and because we want to create some type of composite or some type of alloy, so that we can get the different property onto the surface. So, what happens because of that, the tool edge, cutting edge now individually encounter these phases. So, this is what are these individual phases. Even though it presents in the large scale, what happens in the conventional machining, it is very easy, because many times this particular large phase will cut out through this particular boundary, and that is the region of, that is the region that by which you can cut down this material efficiently in the conventional machining, but that is not happening in the micro machining, because you even without the phase of this alloy, you are end up with the machining at a different phase, because again this defect will play important role that we have discussed previously. Now, what happens because of it creates problem with the forces. Now, variation will be very high in the forces, and again there is energy and the surface integrity is also a problem. So, force is, we have seen that whenever it is encountering a soft material, your force level will be very low. So, if you cut from here to here, what is happening in this particular case, that your force signal will start from 0, then it will stabilize little bit because it is cutting this particular part, then it will suddenly rise it here because you are cutting this part again, then again it will reach to this location because this particular thing will again at this location, then again this part rise and something like this. So, whenever you are getting these particular peaks, you can understand that how many times you have, your tool has passed through these grains or the different phases of the hard material. So, these signatures are important to understand. Only thing that we should analyze this signal correctly, because this is not the only signature by which you are getting this signal. There may be something like that. Suppose you have an end mill cutter and it has a 4 edge, suppose consider, right, and after sometimes what happens, one of the edge is broken, that you are not able to do any cutting. So, when it rotates at that time, what will happen, that it will create a one signal, and when this particular edge will not give any signal because it is already broken. So, you will not get that signal, and then you are getting a 3 peaks continuously, because in this particular 360 you have one angle where the material is not present. That means, this particular location or this particular angle will not remove any material because edge is not present there. So, in this case you also get the signal, but this is in terms of the single point cutting tool, or we consider the only single edge is cutting the material, then you can confidently tell that this is the what is happening in this particular case. Now, coming to the energy, because now energy also plays, because when you are cutting a material through the soft material, you do not need very high powers or spindle or something, but suddenly it encounters this grain, then you have to supply more current to the spindle so that it can overcome the resistance of this hard material, and that is the reason your energy variation will be also large. Again, soft material you do not need so much of energy, again hard material. Surface integrity term is connected with the machine surface, integrity of the machined surface, because what we are getting here, that is important here. Sometimes now you can see here that this particular grain is mostly located inside the grain. So, there is a high chance that this is particular thing is this much. So, this particular part is removed by the cutting tool. Now, consider this in particular, now not this, but let us consider this is the grain. Now, it is exactly opposite to this, that only small portion is located inside the workpiece or inside the machining zone region, but most of the thing is within the uncut chip thickness. So, when these particular things will encounter, then all this grain will go out. So, instead of a flat surface, you are end up with the scoop or the cavity. So, this is what is happening in this case. Right, coming to anisotropic material. Now, anisotropic material means the properties are different in the different directions. So, if you have plane XYZ plane, your material will behave different in different directions. That means, hardness are different and some other properties are also different. So, let us consider this is single crystal. So, this is the 11100 plane, this is 110 plane, and this is the tool and this is the cutting. So, in crystalline material what happens? The plastically yield by the slipping on closely packed planes with different shear stress on slipping on different planes and directions. So, these are the this is our shear plane angle, and these are the different planes. This is the plane and this is also plane. Right. So, crystalline metals plastically yield by slipping on closely packed plane with different shear stress of slipping in different plane and directions. So, we have different planes. So, these are the two different planes. Let us take these two different planes and different directions. So, because the different planes have different, so this 100 plane has this direction and this 110 plane has this direction. So, when your tool is cutting this material, now what will happen, that we have seen that these particular chips are something like this, right. So, these are the stake card of the uncut chip thickness, and then it will remove as a chip. So, wherever this is happening, so these are the different slipping plans. So, if it encounters this thing, at that time your plastic, this whole material will yield plastically in this particular different direction in the different plan. So, anisotropic effect in micro cutting. So, now this we consider as a macro machining, conventional machining, but if you scale down the machining operation, what is going to happen? The preferred orientation of the grains. Now, even if you cut the isotropic material, now in isotropic material also we have seen that we are encountering individual grains. So, we have to also look into the what is the orientation of those grains. So, if you are cutting whether anisotropic material or isotropic material, you have to understand that what is the orientation, whether how much is projected above this line of the uncut chip thickness and how much it is penetrated inside that. That will be decided by whether your tool will cut the material or it will all the material will be scooped out along with the chip. So, this is one of the material property, that profile orientation of the grain is important to understand in the anisotropic effect of the cutting tool. Then the number of grain is very less compared to the volume of the deformation. Now, if you see this particular thing, so this is the deformation zone, and let us put this whole plane as a shear band, and this particular depth of cut let us consider as a 50 micron. Right. So, when you are deforming something a very small scale, you are end up with a very less number of grains. So, that is what is number of grains are very less compared to the volume of the deformation. So, this is the volume of the deformation, you can actually count also how many number of grains are available. So, this creates a problem. So, even if you cut while cutting isotropic material, at micro scale, anisotropic behavior of material plays important role. Correct. So, this example we have taken for the conventional machining, but if you scale down the machining or the micro cutting in such a way that you are encountering individual grain. So, whether you cut isotropic material or the anisotropic material, you have to consider these two things, and when you are talking about these two things, you are actually looking at to the anisotropic material. So, this is what happens when you cut a material at the micro scale. So, what happens in this case? The cutting edge encounters individual grains and crystallographic plane in the direction. So, we know the individual grain we have seen in the last slide, and what crystallographic planes. So, these are the crystallographic planes. So, this is the one plane, this is the 100 plane, and this is the 110 and 100 plane. So, individual grain and crystallographic orientation will encounter during the cutting operation. So, what happens? The material property changes with the crystal orientation, that we will see in the next slide, that if we take one example of a silicon, what is going to happen with this. So, now each plane has a different properties, right. So, we have to find out which one is this particular face is hard, whether this is hard face, hard or soft, or this is soft or hard. So, which face is hard? So, if you consider this is the cutting direction and suppose this face is soft, that means this is the soft material, right. So, this let us write this one is a soft and this one is a hard, right. So, the material is weak in this direction, correct. and it is very hard, or it is very strong in this direction. So, when your tool is moving in this direction, what is going to happen? Your chances are very high that material will be removed in this fashion. So, this whole thing will come out as a chip instead of coming out like in this direction, because this plane is very hard in this case. So, your material removal is different in different plane direction, and that again affect the forces, energy, and the surface finish, because your tool is at one particular depth. The depth will not change with respect during machining operation. So, what is coming across it, that plays important role. So, when it is coming like this in this direction, now you can see that this grain has to be cut out, this grain also, here you are getting the point. So, it is very easy to cut out in this direction, but many times it will not happen this thing. So, you have to cut this grain, again the orientation of this grain plays an important role that we have seen, and then if you continue in this direction, many times you can come across this grain boundary, but many times you may not come across this also. So, energy also required high, because every time you are encountering hard face and the soft face, that is not because of the alloy, but because of the anisotropic nature of the material. And the surface finish is also different, because when the hard face is removed, you may not get the exactly surface requirement as per your desired value, but you can get the something different than other that, and they have to do some type of post polishing or post finishing operations. So, now let us take one example of silicon, that what happens in silicon. The silicon is a face centered cubic with one FCC structure is penetrated to the 25% in all three direction inside the other FCC. So, these are the two FCC structure. FCC means face centered cubic, where one atom is located at the center of the each face and other fours are located at the corner. So, this is the first FCC, and this second FCC, it is penetrating with the 1/4, 1/4, 1/4 in all the three directions. So, basically we consider in ideal situation that it is a FCC structure of the silicon. So, what is happening in this case? Now let us draw this whole thing here. So, this is, let us consider as a block, this is considered as a x direction, this is y direction, and this is z direction. Now, if you cut from this 1 plane, so now what happens, the let us give the name of name also in the different plane. This is this thing. So, now this one is called this one particular plane. So, this is the plane. So, this plane is in the x direction only. So, this plane is called 1 0 0 plane, because this plane is not cutting x and y, or not contacting z and y and z plane. So, this is called 1 0 0 plane. So, this is called 1 0 0 plane, and we have seen here also that how many atoms are located. So, atoms are located 1, 2, 1 at the center, and other 4s are at this location. So, these are the atoms. This without any color in the circle, these are the corner, and whatever is the color at the center, gray color, this is the center part. So, this is 1 0 0 plane. Now, coming to the another one, green color. So, if you consider this plane, correct. So, this is cutting in both direction, one is in x direction, one is in y direction. So, this particular plane is called 1 1 0 plane, but it is not cutting the y, because it is parallel to the y. So, this is 1 1 0 plane. So, when it is cutting this thing, so we know that each and every face has 5 atoms. So, here also it is 1 at the center, here also located one is at the center, here also at the center, here also at the center, and all the other face also let us put one thing at the center. So, when you are cutting this particular plane, so now you can consider 1, 2, 3, now 1, 2, 3, 4, 4 are coming into from the corner part and 2 are from this part. So, one is from the bottom and one is from the top, and these are the two things which are inside, because this has penetrated inside of this 25% from all the direction. So, it may cross this particular thing also. So, this is about the 110 plane. And what is this 111 plane? So, 111 plane is this plane. So, now let us consider your plane is cutting all these three. So, this is called this is called 111 plane, correct. So, now your plane is passing through all these three direction x, y and z. Now, let us see the how many things it has cut down. So, 1, 2, 3 are located at the corner, it is coming in its way, it is cutting from the bottom also. So, it is coming from here, that is coming from here, and from the central part it will come out with the 2 more from the central part because of this penetration. So, now this is the distance between the atoms in this direction. What is happening? Now, let me write this thing also first. So, this is 111 plane. Okay. So, now how to do how to understand the how properties are different in different direction. Now, that depends on how many atoms are located on a particular plane and what is the distance between those planes, distance between those atoms. So, now here lattice distance between the adjacent atom is important. So, this is the distance. Here in this case it is distance, and that means how far this is from this distance, and this is also what is the distance, correct. So, that is the first thing, strong attractive force between the atoms. So, if atoms are located very close to each other, they are strong. Strong attractive force is, that means when they are located close to each other. Okay, that is that thing. And then this is in this case. So, now if you see this diagram, first one, that is a 100 plane, if you see this, just a minute, the distance is very very large here, but if you see here this particular distance, the distance between the two atoms is half of this part. So, it is obviously smaller than this part, and then these atoms are also in its way. So, this distance are very very small again, and this distance are obviously same in this case, but this distance are very very small. Now, coming to the third one, again the lengthwise it is same in this case, but now see this distance is very very large, but this distance are very very equal in all the cases. Apart from this thing, what is another important thing here, that it contains 3 atoms situated at the center. So, now if you see here, so these are the 3 atoms which are located at the center face of the unit cell. So, what happens that if the atom is inside the material, it is very difficult to break or difficult to dislodge from that. The side atoms are very easy to remove. So, whatever those things are located here, these atoms, so these are easy to remove, and whatever this located, this one and this one, these are difficult to remove, that is by etching or by some type of machining operation, that is what is happening. So, here what is happening, so this one is the weakest one. So, let me remove all these things. So, 1 0 1 0 0 is the weakest direction, and this one is the strongest one. Strongest direction. That means it oppose, or it will actually give the more resistance to the material removal mechanism by etching or by mechanical machining also. So, how these things are different? So, let us see the properties. So, these are the properties. So, this is the Miller indices. So, this is in Miller index is one of the ways of identifying the what is this plan, but that we will not discussing here, but we consider 100 plan, that means the face along the x direction, but parallel to the x and y, it is not crossing x and y. 110 that means it is crossing x and y, but parallel to the z, and 111 that means it is crossing all the three direction. Now, if you see the Young's modulus, it is almost 130 is GPa in x direction, but if you see in this case, it is very high in this case, increasing order. And shear modulus is also very low in this case. So, shear modulus, that means your Young's modulus is very high, but shear modulus is low. So, in that case, you are end up with more strong location in the 111 plane. So, what is happening in this 111 plane? Now, you consider you are machining a silicon in this particular direction 100 plane, because whole structure is coming in its way. So, if your face is this one, your tool will smoothly pass through this particular face. But if you are oriented in such a way that you are end up with this particular location, that is the 111 plane, then removal is very difficult in this case. But silicon is mostly micro electromechanical system related operations, mostly it is processed or machined by etching process. So, you put the etching inside of that and put the silicon wafer in that, and then you provide a etching solution. So, it is something like the, suppose this is the silicon and this is the mask, because you do not want to cut the whole material. So, this is called mask, and then you provide a etchant on this surface. So, this etchant will cut down this material, this is the material, and what is happening here, that this is you consider 100 plane. So, it is cutting very easily, but whenever it is reaching this particular location, it is creating always some angle. So, this particular plane is the 111 plane. So, machining or etching in this 100 plane is very easy, but cutting through this direction is very difficult in this case. So, this is one of the examples through which we can understand how anisotropic material will behave in a different fashion compared to the isometric materials. So, what is the specific cutting energy? That let us now see that how much energy we have to spend in cutting the material. So, this is defined as the energy consumed in removing a unit volume of the material. So, let us take this example of a orthogonal cutting. So, your tool is moving in this direction, and let us consider the width of the tool is higher than the cut. So, your this B is the width of the cut, HC is our uncut chip thickness, and this is the V, that is the total part of this part, volume of this part. So, this you are moving in this direction, let us consider this is the V is the velocity. So, now this is the part. So, what is the equation for specific cutting energy in orthogonal cutting? This is what we are getting. So, that is the amount of power or amount of energy required to remove a unit material, right. So, this is the, so Fc is the cutting force, this is the cutting velocity, and this is the BH. So, this whole thing will come in terms of the millimeter cube by second or minute. With the right term, let us put the second. So, this is in millimeter, this is millimeter, this is millimeter by second, millimeter per second, any value. So, this is what you have. So, VV will get cancelled, and then you are end up with the FC divided by B into HC. So, where it depends, that depends on what is the depth of cut, how much is the width. So, obviously, it will cover the area of this part and then how much is the cutting force in this case. So, now if you see this example very clearly, what is happening, that if you reduce the uncut chip thickness, that means if you reduce the cutting depth of cut, then obviously your force will be very, very small, correct. Because here we want to remove a small material, suppose this is the depth of cut and now this is the depth of cut. So, in this case, because smaller you give depth of cut, obviously your force is small. So, that is what is in normal machining operation, but in the actual or conventional machining processes, we know that our HC is not very small in this, that is HC is very small, but our forces are very large, because we have seen that specific cutting energy is very high in grinding, but that is not the case in the machining part. So, in the next class what we will see that how these things is happening, that how the specific cutting energy is very large when you cut a material at the micro scale. So, let us finish this lecture here, we will continue this topic in the next class. Thank you very much. Thank you.